Don't forget to subscribe and ring that bell.
Why, hello, and welcome back to the 2014 AP Calculus AB Practice Examination. We are going to continue Section 1, Part A. We are going to cover multiple choice numbers 11 through 20, and there ain't no calculator for this section. But who cares? You and me, kid, we're smart. Let's get started. You know, I must be living life right because question 11 starts with a graph. I love me some graphs and tables and charts. Oh my. Number 11 reads, for x values from 0 to 6 inclusive, the graph of f prime, the derivative of f, is a piecewise linear as shown above. If f of 0 is 1, what is the maximum value of f on this interval? Okay, let's take a look at what we got and start analyzing. Boom. This is the graph of f prime. So my y value, I should say y is f prime. I automatically do that. I know it says it down here, but I know the y values represent the derivative now. It's a piecewise linear function, and f of 0 is 1. So when x is 1, y is 0. This, my friends, is a coordinate. Train your brain to think that. What is the maximum value on the interval? Well, first of all, let's say I start at a height of 1. This is my height, okay? I am representing my height here. I am starting, okay, 1, 2, 3, 4, 5, 6, whatever. This is 0, 1, 2, 3, 4, 5. And then we got -1. Oh, that's going to be good. And we are going to start right here at 1. How do I know that? Because this. When I start, I'm at 1 already. Okay? But keep in mind, all right, they don't want to know, okay, locations or whatever. What they're asking for is the actual minimum value, not where it occurs. They want to know the actual y value. So how do I figure out? Like, I can tell, for example, when my y values are positive, I'm increasing, okay? When my y values are negative, I am decreasing or moving back down. And then I'm increasing. But how much? The answer to that, if I want to know the value, I need to integrate my derivative to get my value. Okay, that gives me my f value. All right? So integration is area under the curve. And we have some triangles here, which is going to make life beautiful. So let's start right now by finding the area of this triangle right here. All right? This distance is 3. This height is 2. So it's 1/2 2 times 3. Half of 6 is 3. So this area means 3. That means I go up 3 to start. So let's take a look at our dot to the left that represents our height. Okay, after that first triangle, my dot, okay, it's going to move up 3 units to 4. Okay, now let's take a look at the second triangle here. We'll do this red. The second triangle, all right, that is also, in case you can't tell, that goes from 3 to 5.5. I thought it went right to 6, but it went to 5.5. But that's okay. So we'll do this. This distance from 3 to 5.5, we'll call it. That's 2.5, and this height is 2. So it's 1/2 2 times 2.5. Well, a half and 2 cancel, so it's really 2.5. So it drops down. This area is 2.5, okay, the area of this triangle. That means it's going to go down 2.5 units. So now we go back here, and I go down 2.5 units, and I'm right here. And I have this little wedge of a triangle right here. This literally is, I don't know, it's a half by 2. It's 1. I mean, that area right there, it's 1/2 base times height. Well, the base is a half and the height is 2. That's 1/2 of 1 is a half. So it goes back up a half. Okay, so my red dot goes back up a half. All right, so where was it the highest? It was the highest at this point. What was that point? That point was 4. Remember, we started at 1, and then we went up 3 units on this first triangle here. My 1 plus 3 gives me 4, and it's choice D. A lot of explanation there. If you knew this already, you could do this in probably 15 seconds. But if you didn't know it, and I'm assuming that's why you're here, the explanations and drawings all help to hopefully make it more clear. Number 12, let f be the function given by f of x equals 9x. If 4 subintervals of equal length are used, this is important. What is the value of the right Riemann sum approximation? This is also important. For the integration from 0 to 2. Now we're approximating an integral using area under the curve. We are actually going to use RRAM. All right, RRAM. But we're only going to go from 0 to 2. So I'm going to create like this little mock table. Here's my x's, here's my y's. 0, 2. Okay, so why do I have such a big space in the middle? Because I don't want 2 or 3 subintervals. I want 4 equal subintervals. So I'm going to take my distance of 2 from 0 to 2 and divide it by 4, which means every subinterval is going to be a half. Okay, so this is a half. This is 1. This is 1.5, which is the same thing as 3 halves. Okay, so these are my subintervals right here. They go by a half. So let's not forget that y is 9x. So whatever my x is, that's how I'm going to figure out my y value is. Meaning, this one will be 9 to the 0. Anything to the power of 0 is 1. This is 9 raised to the 1/2. If you don't know that 9 to the 1/2 is the same thing as the square root of 9, which is 3, you better study hard for this test. That's a basic thing you should know. This exponent would be 1, so 9 to the power of 1 is 9. Okay, this exponent right here, that's 9 to the 3 halves. Okay, get rid of this. I have 9. The top, which is 3, slides down, and the bottom, which is 2, pops out. I say top down, bottom out. The square root of 9 is 3, but I still need to cube it. 27. All right. And last but not least, 9 with an exponent of 2 is 81, 9 squared. That's our table. We need to do our RRAM with 4 subintervals. All right? First one's going to go from 0 to 1/2. That's my first subinterval. The next one's going to go from 1/2 to 1. I love the color coordination here. The next one is going to go from 1 to 3.5. That's a 1. Oh my God. There you go. And the last one, I don't know, we'll do this fancy orange. Is from 1/2 or 3.5. Excuse me. 3 halves, which is 1.5 to 2. All right. So I'm going to use an RRAM, meaning, and let me clear out some. Let me get some space here. Let's get the big one. Some space here, so we got some room to work with. Okay. Looking at my blue rectangle, I have 2 values, the 1 and the 3, but it's RRAM. I want the right side. It's 3 plus. Look at the red rectangle. I have 2. I have a 3 on the left and a 9 on the right, but I'm using RRAM, or the right one. Plus, Green. Okay, I have 9 on the left and 27 on the right. Again, this is right, RAM. And last but not least, my orange rectangle, I have 27 on the left and 81 on the right. I want 81. Okay, so I'm going to add these all together. 9 and 81 is 90. 3 and 27 is 30. If I add them, it's 120. Do not forget, because 120 is there. Look at that. We need to multiply the sum of our values by whatever the width is. In this case, the width of each one of those rectangles is 1/2. This width is 1/2. Here to here is 1/2, and so forth. So I need to take half of 120, which gives me my 60. Bam. Love it. Easy. Number 13. Strict straight derivative. It is a fraction, so I'm going to use the fraction rule, quotient rule. Low, d high, derivative of high, minus high, d low, derivative of low. I draw a line and I square below. Low d high minus high d low, draw a line and square below. My low is this. My high is the numerator. So it is low, just as it is. D high, the derivative of above, well, that's just 1. Minus high, just as it is, so that's x plus 1, times d low, the derivative of the denominator or below is 2x. I draw a line and I square whatever's below. Currently, it's x squared plus 1, but I need to square that whole thing. So it looks like all of the bottoms except E have x squared plus 1 squared, which is what I have here. Okay, so unless the, oh, that doesn't, so it can't be B. So it's either A, C, or D, unless there's some sort of, algebraic reduction here. The numerator looks like it needs to be simplified. So let's work on that. 1 times anything is itself. So we have x squared plus 1. All right? So I'm going to combine this 2x and the negative. I'm going to say it's negative 2x. Move that out front. Then distribute my negative 2x. So I've got negative 2x squared minus 2x. And let's just combine like terms. We have negative 2x squared and a positive 1x squared. So that's minus 1x squared. We have a minus 2x and a positive 1. The denominator has not changed. It looks like we can't do anything else. So it can't be E or B. So it looks like it's going to be choice C. And that matches perfectly with what we have. Perfect. Okay, 14. This looks like it's going to be a little bit of work here. The velocity of a particle moving along the x-axis is given by v of t, which is sine of 2t, at time t. If the particle is at x equals 4 when t equals 0, what is the position of the particle when time is pi over 2? Okay, so we have velocity. We need to get position. That means I'm going to integrate, all right? Position, velocity, acceleration. This, moving forward, means derivative, okay? Moving backwards is integration, all right? We have velocity. We're moving backward to position. So we need to integrate velocity. But we need to get an exact equation because we got to solve for position with the value of time. And in order to get that exact equation, this is what the initial condition when x is 4 and t equals 0 is going to help us do, to find that exact equation. So let's start by integrating velocity, which is the sine of 2t dt. Whenever you integrate, you must have that dummy variable. Now, all right, if I integrate this, I'm going to get negative cosine of 2t, okay, and then we need the 1/2, so I'll put the minus there, 1/2, all right, plus c. All right, if you want to use u sub, you can. That's a simple one, but it's negative 1/2 cosine of 2t plus c. This equals position. It's x of t. Why am I using x instead of a p? Because x is 4 when t is 0. So I'm using x of t. Okay? And I'm going to use that right now. Okay, when x is 4 at time 0. So I'm going to plug a 4 in for x and a 0 in for time, and I'm going to figure out my c value, because I cannot use this position equation to solve for anything until I find out what my c is. So x is 4, negative 1/2 cosine of 2 times t is 0 plus c. Well, 2 times 0, that's just 0. The cosine of 0. You better know your basic values for trigonometry. The cosine of 0 is 1, okay, times negative 1/2 plus c should equal 4. All right? So what does that mean? Okay, well, let's do down. All right, let's go further. So 4 is going to equal negative 1/2. That's what I get when I multiply, plus c. If I add a half to both sides here, okay, if I add a half, I'm just going to call this 4.5. It's 4.5. That's my c value, okay? That's what's going to go right here to complete my position. So x of t is now negative 1/2 cosine of 2t plus 4.5. All right, I know I got a fraction in there and a decimal. It's fine. We're okay. Now, using this position formula, what's the position at time pi over 2? All right, ready? I'm going to go back to black. When time is pi over 2, so we got negative 1/2 cosine of 2 times pi over 2 plus 4.5. All right, let's do the obvious. These two cancel. Again, know your basic, okay? Know your basic values of trig. The cosine of pi is negative 1 times negative 1/2, and I've got to add 4.5 to that. Negative times a negative is a positive, so I got a positive half plus 4.5. 4.5 plus another half, well, that's my 5. That's my 5. And the answer is 5, which is choice D. Number 15. The function y equals g of x is a differentiable and increasing for all real numbers. On what interval is the function y equals g of x cubed minus 6x squared increasing? All right, here we go. In order to find out if something's increasing, that means the first derivative, or in this case y prime, is positive. So let's figure out what y prime is. We're looking right here. Chain rule. I start by taking the derivative of the outside. Okay, and I leave the inside the same. So I've got g prime. This stays the same times the derivative of the inside now. The derivative of x cubed is 3x squared, and the derivative of 6x squared is 12x. All right. Now, I want to figure out where this is 0, put them on a number line, and figure out my positive and negative values for my first derivative. The problem is, I can set this equal to 0. That's easy. But what about this? How am I going to handle that? You see in the first statement, the first 5 or 6 words, or the first sentence really, the function y of g of x is differentiable and it's increasing everywhere. This part here, since it's increasing, g prime is increasing, will always be positive because it's increasing for all real numbers or everywhere. All right? So I really am now down to the point where I just got to figure this out. Factor, solve, because factoring never goes away. I factor out a 3x, that leaves me x minus 4. And if I t-bone that, this x equals 0. And when I say t-bone, I said the equation equals 0. And this x equals positive 4. So let's start a number line down here. 0, 4. Okay, this is my x value. This is where my y prime will equal 0. Okay, so I'm just going to check in between there and figure out where my first derivative of y is positive. Let's plug in some numbers. We'll pick -1, 1, and 5. All right, now keep in mind, this is always positive. If I multiply something by a positive, it will not change the sign. Okay, so that's really insignificant. So this will always be represented right here by this plus. I've got to take these blue numbers that I wrote in the number line and put them into this right here, I guess. Or I could put it into this. Okay, put it into 3x times x minus 4 and see this sign. Is it positive or negative? All right, and let's start with -1. If I put a -1 in for this x, I get -3. And if I put a -1 in here, I get -5. Okay? So I actually get a negative times a negative, which is a positive. So on the left side of my number line, this will be positive. Let's try throwing in +1 now for these x's. If I throw a +1 here, I get 3 times, if I throw a +1 in for this x in the parenthesis, -4, I get a -3. +3 times a -3 will give me a negative value in between. All right, well, let's try the number 5 now. If I throw a 5 into this x, 3 times 5 will be a +15. And if I throw a 5 into my x minus 4, that gives me a +1. +15 times a +1, well, it's +15. I don't care about the number. I care about the sign. It's positive. So to answer the question, where is it increasing? Anytime it's less than 0 or anytime it's bigger than 4? And if I look at that, that tells me that it's choice A. Okay? A, where it goes from 0 to -infinity to the left, and 4 to +infinity. Those are my two choices. Number 16. It's tricky, but it's easy because we really don't deal with this a lot. The limit as x approaches 3 from the left side of the absolute value of x minus 3 over x minus 3. Okay, first of all, let's try plugging in the number 3. I get 0 over 0. So what I'm going to do is use L'Hopital's rule. And what that tells me is I take the derivative of the top and the derivative of the bottom separately. Okay? The derivative of the top is just 1. The derivative of the bottom is also 1. 1 over 1 is 1. However, the answer is not C. How come? The top, okay, if we have our x's, the top is technically the absolute value. Okay, it's +1 and it could be -1 over 1. All right, so I can either have a +1 or a -1 depending on which side of 3 I'm approaching from. Okay, I am approaching 3 from the left side. That's what that minus on the upper right-hand side of 3 is. And if I'm approaching 3 from the left side, the limit would approach -1, not +1. Okay, so you need that. When I said it's tricky, that absolute value throws a curveball at you. Okay, if I was approaching from the right side, it would approach +1, but from the left side, it's approaching -1. If you want, you can throw in values to the left of 3. I could throw in 2, 1, 0, -1. I could throw any number that's to the left of 3, and I would get a negative value. You know, we've had a lot of pretty rigorous problems in this group, 11 through 20. So 17, for looking as freaky as it is a nice, easy one. If f of x equals a times e raised to the -ax for all values of a that are positive, then f prime of x is. I've just got to take the derivative of our function here. And keep in mind, a is a number, x is a variable. So anytime I have a number here, I'm just going to leave that off, a. Then I want to take the derivative of e, all right? The derivative of e to the exponent is exactly itself. I start by rewriting it, e to the -ax times the derivative of the exponent. Okay? Keep in mind that a is a number, like it's -5 with an x. The derivative of -5 with the x is just -5. It's just the number. So when I take the derivative of this exponent, it's just going to be my -a. Right, well, let's just combine like terms. A times a -a is -a squared, and then we still have our e to the -ax. Choice E. That was simple. When you see A's and B's in there a lot, you're thinking like, what value for A makes this work? What value for B? And it really is a little bit more rigor. But this one, my friends, it was easy. Number 18. A student attempted to solve the differential equation dy dx equals xy with the initial condition y equals 2 when x equals 0. In which step, if any, does an error first appear? Okay, I love doing separable differential equations. All right? So the first thing here is I need to get my y and my dy, okay, alone on one side. So let's do this. Let's make sure we get the thinner one. Yeah, there we go. So I multiply both sides by 1 over y. Multiply this side by 1 over y. So I have 1 over y dy dx equals x. I got to get rid of the dx on the left, so I'm going to multiply both by dx by dx. All right, so at this point, okay, that's a dx. At this point, let me erase what we don't need. This goes bye-bye, and this is bye-bye. So at this point, I've set up doing my integrals. Okay, so now I integrate both sides. And it looks like what I have right here is step 1. Good, check. If I integrate both of these, I get the ln of y plus c equals x squared over 2 plus c. All right, and we don't really write this a lot, even though we should. Whenever I take the natural log of something, it should be positive, so I should write the absolute value bars there. And that is what we have here. In fact, you might say to yourself, it's not what we have there, Visca. Because what they do is, let's call those C on the left C1 and the C on the right C2. They actually subtracted C1 from both sides. So I've got the ln of the absolute value of y equals x squared over 2. When I combine two constants, I'm going to get another constant. So that's really what we have for step 2. So far, so good. Here's where the mistake happens. Let me explain. Let me rewrite what we have. The ln of the absolute value of y equals x squared over 2 plus c. This person took e and set it as a base to these. So this went bye-bye, and I just ended up with the absolute value of y. That's correct. Know your rules for exponents. Okay? If I have two exponents that I add together, That had to come from multiplying similar bases first with different exponents. Okay, that's the only way I can add my exponents together is when I'm multiplying similar bases. Meaning, if I have x squared plus x times x to the fifth, don't I add the exponents? I do. So if I'm adding these exponents, didn't I have to multiply them first? I should have. So ultimately, okay, I should have either this or E is a constant, 2.718. A constant raised to another constant is still a constant. And then I can multiply that times E to the x squared over 2. Okay, so in this person's step 3, they should have either this or simplify it even more for this. They do not have that. You see how they left it as an addition and didn't make it into multiplying two bases? Step 3 is where the error occurs, and that is choice B. Step 3. 2 more problems. We are almost done. Number 19. For what values of x does the graph of y equals 3x to the fifth plus 10x to the fourth have a point of inflection? Point of inflection. That's where the second derivative is equal to 0. And around that 0, my second derivative has to change from either positive to negative or negative to positive. So my sign of the second derivative has to change around that 0. So the first thing I need to do is find the second derivative, set it equal to 0, and figure out where all my possible points of inflections occur. All right? First derivative, 15x to the fourth plus 40x cubed. Second derivative, 60x cubed plus 120x squared. That's my second derivative. Let's set it equal to 0. And my friends, factoring never goes away. I could take out a 60x squared as a GCF and have x plus 2 equals 0. All right. Now, yeah, I did that right. I did that right. So now I've got to solve that, okay? So I'm going to figure out, I'm going to set both of these equal to 0. This x would have to be 0, and this x would have to be negative 2. Let's put this on a number line. 0, 2. These are the x values that make my second derivative zeros. All right? And now I'm just going to check, and I'm going to put some random spots into the second derivative, and I'll use this right here. The great thing about that highlight, the second derivative, is the following. All right? This will always be positive. How come? Because I'm squaring something. I'm taking a positive number, 60, and multiplying it times something squared, which will always be positive. So my 60x squared will always be positive. Always. And I'm going to multiply it times x plus 2. So I just got to figure out what this sign is and figure out if I multiply it by a positive times this, what will the result be? And that will be the result of my second derivative. Let's pick some numbers. Let's pick 2, negative 1. Oh, yeah. Ooh, oh, no, wait. Did we mess up here? Did we mess up? Why do I feel like we messed up? Yeah. Okay, yeah, we did mess up. I just started looking at that saying like, oh, not everything's going to be the same on the negative side. And I don't know if you caught it or not. I wrote a positive 2 there, didn't I? But guess what? Should be negative 2. Ha ha. All right. So let's pick numbers. Let's pick 1, negative 1, and negative 3. All right. Let's start with our 1. If I throw a 1 in here, 1 plus 2 is 3. It's a positive value. Times a positive would give me a positive. All right. So it's positive times positive. So, boom, good. Let's pick the negative one. Okay, this is positive. If I throw a negative 1 in for this x, negative 1 plus 2 is still positive. So it would still result in positive here. So even though there's a 0 here, the sign of my second derivative does not change. So it can't happen at 0. Wherever there's a 0, no, 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 no. Let's check the number -3, okay? Let's check this. This will always be positive times. If I throw a -3 in for this x, I get a -1. That will result as a negative value, and it does change. At -2, my second derivative goes from negative to positive at that point. So -2 is the only place we have a point of inflection, and that's choice B. Number 20, my Lord, this is actually easy, all right? So the limit as x approaches 2 of the ln of x plus 3 minus ln of 5 all over x minus 2 is, well, if I just throw in the number, okay, if I just throw in a 2, 2 plus 3 is 5, and the ln of 5 minus 5 is 0. And if I throw a 2 in here, 2 minus 2 is 0. Anytime I end up with a 0 over 0, I'm going to use L'Hopital's rule. I love using this thing. Okay, I'm going to take the derivative of the top and the bottom separately. All right? So we've used it in a previous problem. Let's use it again. Okay, the derivative of this is 1 over x plus 3 minus the derivative of the ln of 5. That's a constant. It's 0 all over. The derivative of the bottom is 1. Okay. Now I'm going to try and throw my 2 in again. All right. So I get 1 over 2 plus 3 minus 0 over 1. Anything over 1 is itself. And then I end up with 1/5 minus 0, which is just 1/5. Really that easy. Man, if you know L'Hopital's rule, that's going to get you out of a lot of jams. Jam. But you can only use it when you end up with 0 over 0 when you plug in that limit value. Okay? We are done. Took a little bit longer than I liked, 37 minutes, but hey, we got all of our math done, and we got it all done correct, and hopefully we understand it just a little bit better now. Like the video, follow me, because that's the only way you get notifications when I post new videos. And if you want, leave a comment, ask questions, say hi, or recommend another test that I don't have up yet. I will see you guys later. Bye-bye.
Don't forget to subscribe and ring that bell.